Hi there. So in today's lesson, we're going to be looking at this thing called scientific notation. And really, all scientific notation is a better way. So it's better. We'll see why. A better way to write really big or small numbers. And we go, well, how can it be better? Well, it ends up condensing things. And so the kind of overall rule of thumb is that there's only one digit, you'll see what I mean by this, only one digit before the decimal. So a really easy example would be the number 15. It's not 1.5, 15. Well, this is what's called decimal notation. Well, writing it in scientific notation, it's going to end up using a power of 10, and this would be 1.5 times 10 to the 1. But this isn't easier. This isn't more convenient. This is more of a pain than the original. So in most uses, or in kind of most normal instances, it's not very helpful. But in some instances, it ends up being really convenient. And so let's look at maybe a little theory first. So here's some theory. And I want to look at a couple different numbers here. I want to look at 10 to the 0, and we'll look at 10 to the 1, 10 to the 2, 10 to the 3. And maybe from your math class, and you can go find videos explaining this, that anything to the 0th power is 1. And so, but 10 to the first power, well, that's just 10. And 10 to the second power, well, that's 100. And 10 to the third power, this is really what's happening under the hood here is we have 10 times 10 times 10. And that gives us 1,000. And kind of the convenient thing here is that 10 to the 0 has no zeros. But 10 to the 1 has 1 0. Maybe you're starting to spot my pattern already. 10 to the 2 has 2 zeros. 10 to the 3 here, well, that has 3 zeros. And so really whatever the power is, that's how many zeros it ends up having. Is kind of this neat pattern. And so another kind of a little aside here would be looking at 10 to the 100. Well, that's the same thing as, well, if 10 to the 3 has 3 zeros, this would be a 1 with 100 zeros. Now, I'm not going to write 100 zeros. This is already too many. And I'd be here all day, and you'd be really sick and bored with this video. But this would have 100 zeros to it. And the name for this actually is kind of a fun fact. This is actually called anything 10 to the 100 to the 100th power. That is a Google. Not the same as spelling as a search engine, but this is actually where the search engine Google got its name, actually. And because that's a huge amount of anything, a Google of anything. And it's actually kind of estimated that there are only 10 to the 78, or somewhere between 10 to the 78 and 10 to the 82 atoms in the known universe. So we don't even have a Google of atoms in everything that exists today. So now that we kind of have a little bit of this theory down, let's look at some examples for where scientific notation really is convenient, because as we saw earlier up above, it's not very convenient in a lot of kind of day-to-day circumstances. So let's look at this first one. Whatever this is, 150 billion, this looks like. This is meters. This is actually the distance to the sun. And so right now, this is in what's called decimal notation. And even though we don't see it, we know that the decimal is really kind of living right there. And so what we want to do is, like my example up above, we want to make it so there's only one digit before the decimal. And so we're going to have a 1.5 here. We're going, wait, well, we have 150 billion, not 1.5. So how do we keep the true value of the number the same as it originally was? Well, we're going to have to include some powers of 10 here. So I would make this times 10, and well, how many spots did we have to move the decimal to get from here to over here? Well, we had to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this would be times 10 to the 11th power meters. Okay, and so really this is the same thing, but we don't have to have all these zeros kind of clunking around, and it saves us a lot of time and effort by knowing how to convert this really easily. So that's a really big number. Let's look at a really small number. Now, this number, I don't even know what this is, if it's the thousandths or the millionths or what, but we could take the time and look if we wanted to. Now, I'll tell you though, this is the time it takes for light to travel 1 foot. So about the distance between your wrist and your elbow. This is how long it takes light to travel that distance. Well, again, we want only 1 digit before the decimal. So I'm going to have to take my decimal and move it 1, 2, 3. We're going in the opposite direction though. 4, 5, 6, 7, 8, 9. So I'd write 1 point, and now we still have these here. We still kind of have these significant figures. So we'll still have this 0, 0, 0, 6, 9, 2. But now we've gotten rid of all of these zeros in the beginning that are kind of awkward to deal with. So now we'll have times 10. But now if we went in the opposite direction, because this is really a tiny number, well, we counted how many again? I already lost count. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 spaces, but it's from the left instead of from the right over. So this is -9 now, because by having it as a -9, if we were to kind of rewrite this again, moving that decimal 9 spots in the negative direction would get us our original value here, kind of our original number back in decimal notation. So really kind of the rule of thumb here is these powers of 10 that are positive are going to be for the big numbers. These negative powers of 10 are going to be for the small numbers. Now, looking at this next one here, this is a stupendously large number. This is actually an equally appropriate number, though. Actually, this is what's called Avogadro's number, and it's used in chemistry often. It's talking about moles of things, and so if you had 10 grams of carbon or 12 grams of carbon 12, this is exactly how many atoms you would have. Now, at the same time, if you had a mole or this many molecules of water, that's actually about a small sip of water for a typical person. So taking this again and writing it in this scientific notation, we know the decimal is really here, and so we're going to have to move it all the way kind of over in this direction, so the decimal is over here instead. So how do we do that? Well, we're going to count over. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So we're going to have a times 10 to the 23. And what is that number before it? Well, it's just 6.02. So this is a much more convenient way. Imagine having to take this number and multiplying it by this number. You would not want to write all of those zeros. It's much easier to just take the version of them in scientific notation. Now, this last number here we have is actually in kilograms here. That's the mass of a single proton. So protons are pretty light. And we have an even smaller number than the previous one was large. Now, I've already kind of grouped these in threes, so I can see 3, 6, 9, 12, 15, 18, 21, 24, 27, 28. I think I made an error here actually, because I have 1 decimal too many in all honesty. Oh, I see what it is. So this should have been a 1672. That's what it was. So if we still go back and we count 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So we have a times 10 to the 27. And then before that, I just have this 1.672. But now thinking, is this number that we originally had really small or really large? Well, it was a really small number. So we need a negative sign here, because if we wanted to take this in scientific notation and get this original form that we had before, we'd have to take the decimal and move it in the negative direction on a number line, those 27 spaces is really kind of the idea behind it. So that's going from decimal notation to scientific notation. So now let's look at the reverse, going from scientific to decimal. So if I look at this one here, and this actually I believe is the mass of the Earth, well, we know that we're timesing it by 10 to the 24 because that's given to us. So that really means we're just going to take this decimal and move it 24 spots in the positive direction on a number line. Now, that does not mean we have 24 zeros, though, because moving it 1, 2, 3 spaces right there, that takes care of it. So if that's already 3 spaces, we'll have 21 zeros afterwards. So I have my 5, 9, 7, 2, and then we just have to add 21 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. And it's in kilograms. Okay. Now, as we just saw earlier, this next one, actually, that's the one we just had here. So we already know that one. We just have to put those 26 zeros. Now it's times 10 to the negative 27th, but moving it the first spot here, that counts for the first space, really. So we just need our decimal, and then we need those 26 zeros because moving it here is 1, and we'll have 26 more spaces going over to the left is what's really happening here. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. 1, 6, 7. And earlier we had a 2, but we can leave that off this time. And so kilograms again here. All right. Now, this next number, again, we have a small number here, the negative power of 10, not power of 11. I don't know why I have that error there. There we go, power of 10. Means that it's a small number, and the units here are kind of bizarre. This is something we'll look at often in kind of topics dealing with gravity, because this is the gravitational constant. You use this to find the force of gravity on any given planet. And so just like the previous one, we're moving in the direction of the negative on a number line. So that means we're going to be moving to the left looking at this. And so taking my decimal, this is going to count for my first spot. And so really I need, and actually I did make an error here. This power should be to the negative 11th. I just mixed that up. That should be to the negative 11th. I'm sorry about that. And so if this is one spot already, we need 10 more zeros before it. So I'll put my decimal, and we can even just put it here, 6, 6, 7. And so we have already gone one spot, and then we need 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And so I'll put my decimal back over here. And now we have it correctly. And we can check to see that if we bring this back over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, we would get this original value or form of it. So now we have it in decimal notation, not just our scientific notation. And that's meters cubed over kilograms seconds squared. Okay. And now here is another large number for us. So we have our 7, 8, and we're moving the decimal 9 spaces in the positive direction on a number line. And so we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. Our decimal now lives there. We fill in zeros. And we can double check. 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. It works. So if I were to kind of summarize a rule for moving things around in scientific notation, I would probably say something like the following. If this is our decimal, moving it to the right versus moving it to the left, I would say here that we move it to the decimal to the right when the exponent goes down. So that's negative. So what I really mean by that is looking at these examples over here is really that we had to move the decimal to the right. So the decimal here went in the right direction. So the exponent has gone down. It's a negative value is what I really mean here. And that means that when we're going from decimal to scientific notation, that the exponent goes up. It's positive if we have to move the decimal to the left. So again, looking at this one, we had to move the decimal to the left. So here I'm going to the left. And so that means our power of 10 has gone up. It is a positive value. It's just another way to kind of view that. So now that we've kind of got a strong feel for how to convert things in scientific notation, what about actually doing math with them? I'll have to include kind of how to do this with a calculator, but sometimes you won't have that instance, or sometimes you want to be able to go through and make sure that you're understanding and kind of check your work with things. And so really the rule with adding and subtracting, just the general rule that we'll follow here is get both numbers, or all three if you have multiple, with the same power of 10. Get them all with the same power of 10. And so if we look at my first example here, we can see that these don't have the same power of 10. One is 10 to the 7, one is 10 to the 5. Those don't match. But we could rewrite it. We could rewrite it so that both of them have the larger power of 10. And I'll say that the larger power of 10 will work in your favor. So that means I need to write this second number with just 10 to the 7. Well, I can't just change the value of this first number. And what we've done is we've changed the power of 10. We've changed it from 10 to the 5 to 10 to the 2. This is really by timesing by 100, really, is what that is. And so if I've increased it by 100 with the exponents, to keep the value of this number the same, I have to decrease the value of the digits by 100. We want things to balance out. We want the same value. So in essence, if I've multiplied by 100 here, I need to divide by 100 here. And so that's the same thing as taking this decimal and moving it 1, 2 spots to the left. So I would rewrite this as 0.021. And now we have the same power of 10. We're kind of doing decimal gymnastics here. And now what we can do is just take our two values. We can just take this one and just add them kind of the old school elementary school way and have 7.450 plus 0.021. And we just see that we have 7.471, and then we just add on our power of 10 times 10 to the 7. So it's actually really pretty easy. Just get the same power of 10 and then just add or subtract, and then you don't really need to kind of worry about the decimals until you just tack things on. So in this case, we have to remember that a negative 8 power is actually smaller than a negative 5 power. Or in other words, a negative 5 power is bigger than a negative 8 power. So I'll rewrite my larger number the same. And then I have to write this as 10 to the negative 5th. This is the same thing. We have 3 powers of 10 that are different between the two. So really, this is the same as multiplying by 1,000. We have 3 zeros here. And so if I'm multiplying this side by 1,000, this portion of the number, really kind of this portion is becoming this 10 to the 5. I'm multiplying it by 1,000. I need to divide this portion by 1,000. And so that's the same. I'll have my 3, 2, 8 here, but dividing by 1,000, that's going 1, 2, that'd be dividing by 10, dividing by 100, dividing by 1,000 here. So we fill in the zeros, and so that's my value really. Now, again, we have these in the same power of 10, so we can just go ahead and do some old school arithmetic. 9, 6 minus 0.00328. And if you have a calculator, you could just do this on a calculator as well. I just want to show how this actually can be pretty simple and straightforward without a calculator if need be. Now, we want to remember our significant figures though. And I see here that really kind of our rule for significant figures for adding and subtracting is if you don't know it, you can't show it. So I really only know 2 decimal places for both. So my final answer is only going to have 2 decimal places, but we want to do all the math here and then round at the end is the best practice really. And so doing this here, I have to go and kind of my 6 becomes a 5, these become 9s, and then we have a 10 here, and we get a 2 and a 7 and a 6, and then we have 5, 9, 1. And so in the end, I can look here and we can see that this 6 is going to make my 5 here round up. And so in the end, what we'll get is just 1.96 times 10 to the negative fifth as our final answer. So in the end, our final answer, oddly enough, is the same as what we originally had because the thing we're subtracting is so small that it quite literally is insignificant. Kind of odd, go figure. So for our last one here with subtracting, we have to the negative 27 and negative 31. This is actually the approximate mass of a proton here. Let's make it an actual proton. So we have that 7 instead. And this is the mass of an electron. So we're subtracting the mass of an electron from the mass of a proton. And we'll, again, write our power of 10 and leave it the same for our larger value. But then we want to make our smaller value so it has the same power of 10. So going from 10 to the negative 31 to 10 to the negative 27th, this is the same thing as timesing by 10 to the 4. That's a very large number. What is that? In fact, it's 1 with 4 zeros. So that's multiplying by 10,000. So if we're multiplying by 10,000 on the exponent, we need to be dividing by 10,000 on the decimal itself. And so if we multiplied 4 spaces of 0 by it, we need to actually divide by 4 spaces of 0 is another way to kind of think of it. And so we have our 911 here, and our decimal originally lived there, and we'll move it 1, 2, 3, 4. And we'll place our zeros, and we'll do something very similar. Now, in case of just kind of for time's sake, I do have a calculator here, and what this gives me is something very similar to what we just got above. If you subtract these two from each other, 1.67 minus this 0.000911, we end up getting 1.669089. And following our sig figs rule, this 9 makes the 6 round back up. So we end up having still 1.67, and our power of 10 is times 10 to the negative 27. So again, like earlier, this value is just totally insignificant, even though we went through all the work with it. Now, I want to look at multiplying and dividing since we've done some practice with addition and subtraction. Now, this one's kind of interesting. There's kind of a 2 different rules here for if you're multiplying. If you're multiplying, you're going to add the powers of 10. So add powers of 10 if multiplying. Similarly, you'll subtract powers of 10 if dividing. And really, that's the powers of 10, how we deal with it. As far as the decimal itself, just multiply or divide the decimals. Now, when I say decimals, I mean whatever's in front of the power of 10. I know that there aren't actually decimals on the 4 and the 3 here, for instance. I just want to make that abundantly clear. So following our rule with this, and you could check this with a calculator, well, it says add powers of 10 of multiplying. So I'm multiplying 4 times 10 to the third. So 4 times 10 to the third. So that's just 4,000. But then 3 times 10 to the 6th, well, that's 3, and then 1, 2, 3, 4, 5, 6. That's 3 million. I'm multiplying these two numbers together. And we said that instead of having to struggle with all these zeros, we can just add powers of 10. So we're just going to have a times 10 to the 9. Well, that's convenient. And then it just says multiply or divide the decimals. So multiplying 4 and 3, I get 12. That's actually it. We're done, except that this is no longer in scientific notation. If we look back up at the top, scientific notation means there's only one digit before the decimal, like this 15 becomes 1.5 here. So we need to actually change this 12 into scientific notation now. So doing that, we just have 1.2. So I move the decimal one spot to the left. I'm essentially dividing by 10, but I can't lose the true value of this number. So if I divided by 10 with the left side here, I divided to go from 12 to 1.2, I need to include an extra power of 10 with my power of 10 here. So instead of 10 to the 9, it's going to be 10 to the 10 because these are the same values. We have an extra power of 10 here, but we lost a power of 10 here. And so we have really like a times 10 to the negative 1 and then a times 10 to the 1, and these really just cancel each other out is really the idea for it. So looking at this next example, we're multiplying again. Well, it says we're multiplying. It says add powers of 10 of multiplying. And so this is kind of an odd thing. Well, we have 10 to the negative 2 and 10 to the 2. Well, 10, we can look at it this way, 10 minus 2 plus 2, that just becomes 10 to the 0 because negative 2 and positive 2 just cancel, 10 to the 0. And then multiplying or dividing the numbers, we just get 25. 5 times 5 is 25. So really, we again have the same issue as with this 12 up here, though, where we have to get it back in scientific notation, where it will become a 2.5. We've taken the decimal and moved it one spot to the left. We've divided by 10, essentially. So if we've divided by 10 with the decimal portion here, we need to multiply by 10 with our power over here. So it will become times 10 to the 1. Now, we have a bit of division here. We have some division now, finally. And so looking at this, we're dividing, and it says our division rule is subtract powers of 10 if dividing. So subtraction, that's pretty easy. We have times 10, 9 minus 7. 9 minus 7 just gives us 2. That's easy. When it comes to multiplying or dividing the decimal portion, as we have here, well, we'll have to do 8.22 divided by 2. And so I have my 8.22 here. We'll divide it old school style by 2. That gives us a 4. So we have 8. All right, 0. The 2 comes down here. We have a 1. And then 2 times 1 gives us a 2 again. So we have 0. And then this 2 flies down. We have 2 again. We have a 1. We can't forget the 0. So we just get 4.11 times 10 to the 2. So that's actually a pretty easy one as far as how to do the math itself on it. Now, we have some more multiplication, but now we have really small numbers instead of really big numbers. Well, the neat thing is that we still are just multiplying, so we have add powers of 10 of multiplying. And I would like to mention here, though, that really, when you have something to a negative power of 10, that really means you're dividing by it. I know that sounds weird, but this entire value, we could rewrite as 1 divided by 9.11 times 10 to the 31, and then 1.6, and let's make this the mass of a proton again. 7 times 10 to the negative 27, and it's not negative though now, it's positive 27. So really, having a negative here means it's in the denominator of kind of the fraction itself, but oftentimes it's just easier to deal with it like this. And so we'll kind of just leave that aside, and maybe look at this as a check for our work, really. Now, since we're multiplying, we're just going to add the powers of 10. Well, it's easy to kind of add negative 31 and negative 37. That just gives us negative 58, because 1 and 7 is 8, and 3 and 2 gives us 7 here. Now, as far as multiplying the rest of it, I'll save you the tedium of having to multiply, but we could have just done 9.11 times our 1.67, and you would find that we end up getting something like, I think it's 15.2137, something like that is what we should get. Now, because of our significant figure rules, though, we can see that this has 3 sig figs, this has 3 sig figs, so our answer really should only have 3 sig figs here. So when I look, we should really be getting rid of this part. We don't have enough information to know that. So in the end, we'll just write this as 15.2. But again, we have this issue where this is actually not in scientific notation. We have to fiddle with the power of 10. And so we're going to have to take our decimal and move it to the left 1 space here. And so I can see that we've divided by 10 to get 15.2 becomes 1.52. And so since we've divided by 10 on this side, we have to multiply by 10 on this side. But it gets a little dicey because we have negative powers of 10. And so multiplying this all by positive power of 10 gives us times 10 to the negative 57, in fact, because we've increased it, and this actually is a bigger number than that original number. 10 to the negative 57 is larger than 10 to the negative 58. Now, for our last example here, we're dividing again. So following our division rule, we'll just subtract the powers. That's all we'll do. And so 42 minus 11, well, that just becomes 31. So we have 31 here. And then we have to go and divide 3 by 4. Well, just thinking really easily about this, 3 over 4, that's like 3/4 out of a dollar. That's 0.75. And if you want, you can go and do the math for it and kind of go and divide by 4, and you'll get a 0, and then you'll get a 7 and a 5, and it's the same thing. So we end up having 0.75 here, and I know I am ignoring my sig figs. I know that this has 1 and this has 1, but I don't want to leave it as 8 right now personally, just for sake of example. But now, again, this is not in scientific notation anymore. We don't have 1 digit that's non-zero before the decimal, so we have to change this again here. We have to go ahead and actually write this as 7.5. So now we've moved the decimal to the right. That's the same thing as multiplying by 10. And so we've multiplied by 10 on the left side. We need to divide by 10 on the right side. It's kind of like a balancing act that we're consistently doing. And so removing a power of 10 here just ends up giving us 10 to the 30th. And so that's really it. That's how to do our subtraction, our division, large numbers, small numbers, just converting between these, doing the addition, the multiplication and division, and really kind of some theory behind it. I hope that makes sense.